Welcome to the fascinating world of black holes, the most mysterious objects in the universe. Out there, scattered among the billions upon billions of stars, lurk regions of space-time where gravity is so strong, so inescapable, that nothing, not even light itself, can break free. These are the cosmic abysses we call black holes. Today, we'll embark on a journey to explore what truly happens inside these enigmatic objects, peering beyond the event horizon and challenging our very understanding of time and space. Imagine a place where the fabric of reality is stretched to its breaking point, where the laws of physics as we know them cease to hold sway. It might sound like the stuff of science fiction, but these cosmic monsters are very real, and they hold secrets to the universe's most fundamental workings. Join me as we venture into the heart of a black hole and unravel the cosmic mysteries it holds. So what exactly is a black hole? Imagine the most extreme gravitational powerhouse you can, a region in space where matter has been squeezed so tightly that it creates a gravitational pull so strong that nothing, not even light, can escape. These cosmic traps are born from the death throes of massive stars far larger and heavier than our own sun. When these stellar giants exhaust their nuclear fuel, they can no longer support their own weight. The core collapses in on itself, and if the star is massive enough, this collapse continues unabated, creating a singularity, a point of infinite density. That's the heart of a black hole, a singularity. But the black hole's reach extends far beyond that point. Surrounding the singularity is an invisible boundary called the event horizon. This is the point of no return, the cosmic Rubicon. Once you cross it, there's no coming back, not even for light. But black holes aren't just one size fits all. Oh no, the universe is far more creative than that. We've discovered that they come in a range of sizes. Stellar mass black holes, the most common type, are formed from the collapse of individual stars. Supermassive black holes, on the other hand, are millions or even billions of times the mass of our Sun and reside at the centers of galaxies, including our own Milky Way. And then, there are the primordial black holes, hypothetical objects thought to have formed in the very early universe, just moments after the Big Bang. These ancient relics could range in size from microscopic to astronomically large. Imagine approaching a black hole, venturing closer and closer to its grasp. As you draw near, you'd notice something truly bizarre happening around the black hole. The fabric of space-time itself is being warped. You see, gravity, according to Einstein's theory of general relativity, isn't a force in the conventional sense. It's the curvature of space-time caused by the presence of mass and energy. And black holes, well, they're like placing a bowling ball on a trampoline. They create a deep, deep well in the fabric of space-time. The event horizon marks the point where this curvature becomes so extreme that all paths through space-time lead inwards, towards the singularity. Not even light, the fastest thing in the universe, can escape its clutches. It's like trying to swim upstream against a current that's always faster than you, no matter how hard you struggle. This warping of space-time around a black hole is what gives them their eerie appearance. Light, as it passes close by, gets bent and distorted, creating a visual effect we call gravitational lensing. It's like looking through a cosmic funhouse mirror, where the images of distant stars and galaxies are stretched and smeared around the black hole's silhouette. The event horizon itself is not a physical boundary, not something you could touch or see. It's simply a region in space where gravity's pull becomes inescapable. Cross that invisible line and you're committed to the black hole's bizarre and ultimately destructive embrace. Now let's talk about what would happen to you if you were to fall into a black hole. It's not a pretty picture, but it's a fascinating thought experiment that reveals the extreme nature of these objects. As you approach the black hole, you'd experience a phenomenon known as spaghettification. Imagine this: your feet, being closer to the black hole, would experience a much stronger gravitational pull than your head. This difference in gravity, called a tidal force, would stretch your body out like a cosmic piece of spaghetti. The closer you get to the singularity, the more extreme these tidal forces become. Your body would be elongated and compressed, stretched thinner and thinner until you're essentially a stream of subatomic particles spiraling towards the unknown. But it's not just your body that would be affected. Time itself would behave strangely near a black hole. According to Einstein's theory of general relativity, time slows down in stronger gravitational fields. This effect, known as gravitational time dilation, means that time would pass more slowly for you as you fall into the black hole compared to someone observing from a safe distance. To an outside observer, you would appear to slow down as you approach the event horizon, your image redshifting until it fades from view entirely. You would seem frozen in time, forever poised at the edge of the abyss. At the very heart of a black hole, shrouded by the event horizon and beyond the reach of any telescope, lies the singularity, a point of infinite density where the laws of physics as we know them break down. Imagine all the matter that ever fell into the black hole, crushed and compressed into an infinitesimally small point. It's a concept that stretches our understanding of physics to its limits. Inside the singularity, our equations simply don't work. Gravity becomes infinitely strong, space-time curves infinitely, and our current theories can't predict what happens. Some physicists believe that singularities, as we currently picture them, might not actually exist. They argue that our understanding of gravity, based on Einstein's theory, is incomplete, and that a theory of quantum gravity is needed to fully describe what happens at these extreme scales. Quantum gravity seeks to unify Einstein's theory of general relativity, which governs the universe on large scales, with quantum mechanics, which describes the world of atoms and subatomic particles. It's a quest to find a single, elegant theory that can explain the universe from the smallest to the largest scales. The singularity, therefore, remains one of the biggest mysteries in astrophysics. It's a place where our current understanding of the universe breaks down, and where new physics, new insights into the fundamental nature of reality, might be waiting to be discovered. Black holes, with their extreme gravity and mind-bending physics, have captured the imaginations of scientists and science fiction writers alike. They've sparked countless theories and speculations, some more grounded in reality than others. One intriguing possibility is that black holes could be portals to other universes or other parts of our own universe. These hypothetical shortcuts through space-time are known as wormholes. Imagine a tunnel connecting two distant points in space-time, allowing you to travel vast cosmic distances in an instant. While wormholes are theoretically possible, they remain highly speculative. Then there's the concept of white holes, the theoretical opposite of black holes. While nothing can escape a black hole, nothing can enter a white hole. They're often depicted as spewing out matter and energy like the Big Bang in reverse. Some physicists believe that black holes might not be entirely black after all. They theorize that black holes could slowly leak out radiation over incredibly long timescales, eventually evaporating completely. This process, known as Hawking radiation, is named after physicist Stephen Hawking, who first proposed it. Could advanced civilizations, far more technologically advanced than our own, harness the power of black holes? Could they use them as sources of energy, or even as gateways for interstellar travel? These questions remain firmly in the realm of speculation for now, but they highlight the profound impact black holes have on our understanding of the universe and our place within it. The answer, surprisingly, might not be as simple as you think. While nothing that crosses the event horizon can ever return, black holes aren't entirely one-way streets. In the 1970s, Stephen Hawking made a groundbreaking discovery. He found that black holes aren't entirely black after all. Due to quantum mechanical effects near the event horizon, they actually emit a faint thermal radiation, now known as Hawking radiation. Think of it this way: empty space, the vacuum, isn't truly empty. It's teeming with virtual particles, pairs of particles, and antiparticles that constantly pop in and out of existence, borrowing energy from the vacuum itself. Near the event horizon of a black hole, these virtual particle pairs can be separated by the intense gravity. One particle might fall into the black hole, while the other escapes into space as Hawking radiation. This process is incredibly slow, especially for large black holes. A black hole the mass of our sun would take longer than the current age of the universe to evaporate completely through Hawking radiation. But Hawking radiation has profound implications. It suggests that black holes aren't eternal prisons, that they slowly lose mass and energy over time. It also raises intriguing questions about the fate of information that falls into a black hole. Does it disappear forever, violating one of the fundamental principles of quantum mechanics? Some theories suggest that information might not be lost but rather encoded in the Hawking radiation emitted by the black hole. This information paradox remains an active area of research, pushing the boundaries of our understanding of black holes and the universe itself. Thank you for joining us on this journey into the heart of a black hole. We've peered beyond the event horizon, explored the extreme physics at play, and pondered the mysteries that still remain. Black holes are perhaps the most enigmatic objects in the universe, challenging our understanding of gravity, space-time, and the very nature of reality. But they are also a reminder of the vastness of the cosmos and the incredible discoveries that await us. The universe is full of mysteries, and black holes are just one of the many wonders waiting to be explored. Stay curious and keep looking up. The cosmos is out there, waiting to be discovered.